Hello everyone, my name is Kshitish Parikh and today I'm going to discuss the better lesson and many related things in the field of AI. So what is better lesson? It is a short blog written by Richard Sutton, a pioneer in RL in 2019, and it's one of the most important blogs I personally feel. But the problem I see is that it is discussed again and again on Twitter, but people don't get the nuances written in it. I think people have a shallow understanding of it. So today I would like to discuss, and I just got inspired because Noam Brown again talked about the better lesson today, and people have been posting about it. So I thought it's time to discuss it again, and then we will see what all these people are also saying. So before we see this, I think people lack a lot of context or understanding of intelligence, and I think we'll start with that. Okay, so we as a research community in AI has been a field from maybe 1956 you can see, or 55, the summer conference you can say, which was started by Minsky and others, or even before that there have been aims of making machine intelligence. You can go 200-300 year back to a lot of time, but the thing is nobody has proposed a definition of intelligence, or you can say people have proposed, but we don't have a consensus on the definition of what intelligence is. And the problem is this leads to us having many implicit biases about what we feel intelligence is, but it is not actually intelligence, and I think that is one of the blocks which is stopping us from solving intelligence. So in 2019, Francois Chollet released a paper on the measure of intelligence, and I personally find the definition of intelligence in it to be satisfactory. So let us discuss that. Let me just go to the okay. So what is the definition he proposes? Okay, so first of all let me just give an intro about this paper. So this paper also says that there has been a quest to solve intelligence, but we actually have never defined intelligence, and that has been lacking as a north guiding star to take us, like for any scientific field we need to have some goals and a guiding star that this is our goal, and doing this will lead to us intelligence. We have some had implicit biases, like maybe solve this benchmark, or maybe solve chess, solve these games, and it will lead to intelligence, but none of that has happened. And I feel many people lack the perspective of AI history, so I think this is a must read for any person in the field of AI to get to know what is the has been the field of history of AI, and still we have not made much progress toward intelligence. We have done a lot of automation, and I think the more you read it, and he will talk about many things, Chollet, and then you can go and read more about all those things, like what has been what about maybe knowledge based systems or symbolic AI, and you get a better understanding of the whole field of AI. Okay, so what is the definition Chollet proposes? The intelligence of a system is a measure of its skill acquisition efficiency over a scope of task with respect to priors, experience, and generalization difficulty. So the first difference is, compared to everything which has been done till now, Chollet is saying intelligence is skill acquisition efficiency. It is not skill or performance on a particular task. This is a very different thing. So if we have a particular task, here I'm just gonna take a task like solving a maths paper. So we are not interested in if somebody gets 100 out of 100. We are interested in how efficiently they are able to get a particular score, 100 out of 100. So what are the things we need to take in consideration? A scope of task. So any AI system we have, it will be only able to do some task which we have trained it for. But what we are interested in, even if you have trained it in one task, can it do many other similar tasks? So that is one thing. But before coming to that, so if we are talking about skill acquisition efficiency, what should we look into? We should look into priors. So priors are maybe shortcuts or hints, or you can say things AI researchers have added into the AI system to make it easy to solve that particular task. So there are some things which you can do which would help in this particular task, but not in a generalizable way to other tasks. So those are priors. So for example, CNN have translation invariance that is inbuilt because of the way the architecture and the filter, the same filter moves around the whole image. So if we have two systems where everything is equal, experience, generalization, difficulty, and performance, and one has one is a CNN based system which has translation prior, and another system which does not have any prior. then it can be said that the second system, which has no prior, is more intelligent, because it has to discover the prior of translation invariance on its own. This is a very important point, and it will come up again in the better lesson, so I want you to keep it in mind. So one is prior. Basically, what hints are you giving for the task which don't help in a general way but are only helpful for this task? Experience is the training data. So if we have two systems which are getting 100 out of 100 in some maths test, but if one has been trained on a lot more data, then it is less intelligent, because it requires more data to reach the same performance. So that is experience. Like if we talk about a human example, I don't want to anthropomorphize or talk about humans, but in general, if you have two students, both are getting 100 out of 100, but one studies 2 hours and one studies 10 hours to get the same score, then you would say that 2-hour one is more intelligent, or is more able to learn quickly or better. And generalization difficulties, so basically how difficult is it to solve the task, and how much can it generalize with respect to similar task. So if I can just find the figure, just give me a second. I don't know if it's below or okay, I think it's above. Okay, definitely not above. Okay, so okay, also I'll talk about ARC, just give me a second. So if we look at this, we have two systems where it is trained on some known situations. So the first system is only able to be able to deal with situations which are in this smaller domain, while the second one is able to deal with a longer domain of situations. So the second one is more intelligent. So basically it can extract more things out of the same information, out of the same training data, right? If you have somebody who's very smart, after reading the same essay, they would be able to make a lot more conclusion or insights compared to somebody who is less intelligent. I mean, this paper has a lot of things which are very important. I think this must be a must read for anyone who wants to solve intelligence, so I won't go into it now, but the one thing I will say that shows that the value of this paper is, so this paper came out in 2019, and he was talking about what is intelligence and actually how to test intelligence, because it is skill acquisition efficiency. You can't just test on a task. Sholay proposes a benchmark, which is ARC, which is abstraction and reasoning corpus. And the thing about this benchmark is, there has been, as far as I am aware, other than one weird paper which got 30% performance on this, but was an open source, so you can't verify. No VLMs or LLMs or whatever state of the art AI systems we have has got more than 10% performance, and it's a very simple task. So you are basically, if I think this examples would be better, figure 7 would be better. So basically, and humans are able to solve this very easily. So what you are given is, this is your input, this is your output. So basically there is a red set of blocks, blue set of blocks, and there is some operation happening which leads input changing to output in this way, and you are basically asked, if this is the input, what should be the output. So you can pause the video and think about it. You can look in the paper. These are very simple things which a very young child would be able to do, but today's system are not able to solve it. Okay, so this is the first important thing. So intelligence is about skill acquisition efficiency and not just about task performance. Okay, now we'll get back to this, but let us go and discuss the better lesson, word by word. The better lesson. As I said, it was written by Richard Sutton in 2019. Okay. The biggest lesson that can be read from 70 years of AI research is that general methods that leverage computation are ultimately the most effective, and by large margin. So what he's talking is that if we have a particular task, the history of AI tells us that methods which are able to use a lot of compute, they at the end of the day, or as of 2024 you can say, they perform better than other methods. The ultimate reason for this is Moore's law, or rather is generalization of continued exponential falling cost per unit of computation. Moore's law is basically compute is becoming more cheaper and cheaper, therefore we have more GPUs, better GPUs, and we are able to train larger models. Most AI research has been conducted as if the computation available to the agent were constant, in which case leveraging human knowledge would be one of the only ways to improve performance. but over a slightly longer time than a typical research project, massively more computation inevitably becomes available. So I think one implicit bias researchers are trying to do is that they assume that because the computer is fixed, they are not interested in how scalable their method is or AI system is. By scalable is not all AI systems will be able to use more compute efficiently or equally efficiently. Maybe as of now, like transformers are able to scale more compared to RNNs or LSTMs. Even we had RNNs and LSTMs are way older, but we are not able to create such larger models. So transformers are able to scale much more, and so you can say they are able to utilize the computation better, and they perform much better than RNNs and LSTMs. Seeking an improvement that makes the difference in the short term, researchers seek to leverage their human knowledge of the domain, but the only thing that matters in the long run is the leveraging of computation. I think that's self-explanatory. The two need not run counter to each other, but in practice they tend to. Time spent on one is time not spent on the other. Now this is very important. As a researcher, we have limited 24 hours in a day. So whatever approach you are optimizing for, it means you will not be optimizing for the other approach. There are psychological commitments to investment in one approach or the other, and the human knowledge approach tends to complicate methods in ways that make them less suited to taking advantage of general methods leveraging computation. There were many examples of AI researchers belated learning of this bitter lesson, and it's instructive to review some of the most prominent. So he's talking about how some AI researchers were not interested in using compute, but were interested in adding priors from the previous terminology we discussed of how human knowledge, what can we tell the AI system from before or help it, hard code it, that makes the task easier and it will perform better. That was their hope. But in the end, compute won. With I would say with asterisk, I'll discuss the asterisk mark later. In computer chess, the methods that defeated the world champion Kasparov in 1997 were based on massive deep search. At the time, this was looked upon with dismay by the majority of the computer chess researchers who had pursued methods that leveraged human understanding of spatial structure of chess. But natural, it didn't work out for some researchers, so they were bitter. That's where the bitter word comes in the bitter lesson. When a simpler search-based approach with special hardware and software proved vastly more effective, these human knowledge based chess researchers were not good losers. They said that brute force search may have won this time, but it is not a general strategy. In any way, it was not how people played chess. These researchers wanted methods based on human input to win and were disappointed when they were not. Now this is a very important paragraph which I think both set of people get wrong, and people need to understand it from Schole's perspective. So the people who won, who used compute and defeated Kasparov or conquered chess, and people who lost, both of them don't understand something very important. Both of them are right in a way. So first of all, yes, it is true that the compute-based methods we have, whether that be the 1997 method used or today we have Google DeepMind's RL algorithms with self-play, AlphaZero, and I forgot the name, but yeah, they use a lot of self-play, they use a lot of compute, and they are able to beat in chess. But the problem is, when you're talking about chess, you have defined a task. Now, when you have defined the task as Schule talk, then it doesn't become intelligence. It becomes only solving a specific task. So when you want to solve a specific task, that's good. If that's your goal, that's no problem. But that does not have anything to do with intelligence. It's almost orthogonal. So when you solve a task, you can always add a prior. Now, chess is such a game that adding priors of what humans believed, which the other researchers tried, did not work out. But having a model which was using a lot of RL and lot of search, which move to play and back propagating and figuring out which move was the best, worked out to be the best. So it is true. The point that it is a brute forcing technique and it is not a general strategy. Basically, see, we have conquered chess in 1997. If I remember, Go was solved in, it's already written 20 years later. Why did it take 20 years? That's also a thing. It's just computational complexity is higher, and we'll get into that. But main point is, even after solving that, we have not been able to do simple tasks. So if I refer to Moravec's paradox, which this is very important, which people need to know about from AI history. It says that the tasks which are easy for humans are hard for AI and vice versa. So what are some tasks which are easy for human but hard for AI? So the three main tasks he lists are mobility, dexterity, and perception. So even today, after solving so many games, DeepMind has solved Dota, and so they have so many models which perform good on so many games. We do not have a simple robot which can make a simple coffee or can go out in a simple environment and stay alive in the environment. One thing would be, I would refer people to go to refer to the DARPA. So DARPA conducted a robot. I would say, I don't know, not a conference is not the right word. Basically, they challenged researchers to make good robots from 2013 to 15, and it was a complete failure. And I would urge people to look at, actually, even after the state of the art, they were the best researchers with the lot of money, with the best method, and it couldn't work out. And today even we don't have robots which are able to which have mobility or dexterity, and even perception is not solved in my opinion, because we have adversarial networks and our models make many very stupid mistakes. And the fact that adversarial examples exist and they are such a big subspace, and if there are papers, I can't remember the name, which show that if you say a cat, the models actually don't see a cat, but they are seeing something very different. So if I remember the example, instead of seeing a black and a yellow and black bus, the models actually just see yellow and black stripes. So these things have not been solved even after 80 years and so much compute. So it is true that we solved chess, but this was task solving, so this had nothing to do with intelligence. And it is true that humans don't solve it, because since humans cannot optimize for chess in a particular way, like internally, like of course if I am a human I can use an external instrument such as this chess algorithm we have created to optimize for chess, but internally I cannot suddenly just increase my compute or do a deep breadth search or depth first search, right? I have limitations in my memory. So therefore I have to use intelligence and reasoning. Basically the point is, they were right that this is not a general strategy and this is not how humans solved. So the Sholay also talks about that even after solving chess we are nowhere close to solving intelligence or have methods which generalize well. So this is a point no one talks about, that if you want to solve a task, good, everything good, put the priors, give a lot of compute, good, but your methods will only work for the task. They will maybe some similar, so the level of generalization is very low. Generalization is again a spectrum. Okay, next. A similar pattern of research progress was seen in the computer Go, only delayed by further 20 years. Enormous initial efforts went into avoiding search by taking advantage of human knowledge or the special features of the game. But all those efforts proved irrelevant, or worse, once search was applied effectively at scale. Okay, one more thing. People need to understand games are formal settings. By formal settings, what I mean is they have well-defined moves which are logical, what is illegal, and you have a well-defined reward systems. Real world is very messy. There is no task you can say a human optimizes for. I mean, you can say survival. What did you write the task as? So games are very formal setting, and what we have realized from AI history is that games are actually very easy to solve. The real world is very complex, where any random things can happen. That is the problem with robotics. Anything can happen. So when you have automation, very well defined setting, I mean automation is used everywhere, in making cars, in making the chips we have. Automation is very common, but that is very well defined control setting, that this is the only thing which you would expect your system to encounter, and you are controlling for failures over there. Over here in robotics, we want agents which have agency, which can deal with randomness, and we have not been able to solve that. And I think only intelligent beings can deal with randomness. Also important was the use of learning by self-play to learn a value function. Again, self-play is only possible if you have a well-defined setting and you interact with the real world. There are a lot of people who believe synthetic data will work. I don't think it will work. They are misguided, but I won't go into that now. Anyways, search and learning are the two most important class of techniques for utilizing massive amount of computation in AI research. Okay, you want to use compute, you use search and learning. One more important thing is to know, in the history of AI, the learning word was not prevalently used till the start of 1980s, if I'm correct. So before that we had knowledge based system, basically where you had a set of facts and you had some rules which you apply on these facts to come to more facts or conclusions. So those were knowledge based systems, or symbolic AI you can say. Basically you are manipulating symbols. Now that is okay, but the only problem is, how do you have symbols for everything? Like You can have a symbol for the common is all men are mortal, and I am a man, so therefore I am mortal, something like that. That symbol is okay. But how do you have symbols for abstract thing? Like when I say cat, you know what a cat is, I know what a cat is, but it's hard to describe. You can say maybe it has whiskers, it is of this color, that way. But I can always give you a counter example. Like if there is a cat and I cut its whisker, is it not a cat? It's a cat. So the problem is you know what a cat is intuitively, but you cannot tell me what that is. And that is the important thing which is talked about in the last paragraph of better lesson, which I think I don't know why people don't talk about it. I think that is the more important lesson. The important lesson is not compute, but I'll get about it, that the contents of how our mind work is inaccessible to us. Okay. Anyways, search and learning, yeah. In computer Go as in computer chess, researchers' initial effort were directed towards utilizing human understanding, so that less search was needed, and only much later was greater success had by embracing search and learning. Okay, so as I was saying, learning is a new thing which was not initially incorporated in the AI paradigm, which I think is one step in the right direction. That you want the models to learn on their own, but still we have not gone full learning, which I will explain. In speech recognition, there was an early competition sponsored by DARPA in 1970s. Entrants included a host of special methods that took advantage of human knowledge of words, phonemes on human vocal tract. On the other side were newer methods that were more statistical in nature and did much more computation, such as hidden Markov models. Again, the statistical methods won over the human knowledge-based methods. This led to a major change in all of NLP. Gradually, over decades, where statistics and computation came to dominate the field. The recent rise of DL in speech recognition is the most recent step in to this consistent direction. DL methods rely even less on human knowledge and use even more computation together with learning on huge training sets to produce dramatically better speech recognition system. As in the games, researchers always try to make systems that work the way researchers thought their own mind work. This is the most important statement here, and I will get to that. They tried to put that knowledge in these systems, but it proved ultimately counterproductive and a colossal waste of researchers' time when, through Moore's law, massive computation became available and means was output to put it to good use. Okay. So that is true. If you go to Lighthill's report, it is a report by the British government section Lighthill, a scientist, to make a report on the current state of AI in the 1970s, if I'm right. So basically that report talked about how AI was trying to make progress, but there were no applications. So the things which was talked about was such as speech recognition, basically speech to text, or translation systems, or or handwriting recognition systems. So all these three tasks are solved if you know. Like we have object character recognition, Google Lens, we all use it. We have it as of 2024. The speech to text model are very good, at least in English. And even machine translation, I won't say it's that good, in like it makes mistakes, but I would say it's very good compared to what we have had before. So yeah, compute has won. Okay, that is true. But again, these were specific tasks where you inserted specific priors for those tasks, and only those tasks worked. But so later I'll get to this line that worked the way researchers thought their mind worked. Before that, let me just go for two more paragraphs and then I will come back to it again. This is very important. Wait for it. This is not what everyone discusses. People talk about scaling or do computation, increase compute, get more GPUs. That is okay, but I'll go to that. In computer vision, there have been similar patterns. Early methods conceived of vision as searching for edges, generalized cylinders, or in terms of shift features. Basically, they were hand-engineered ways by scientists of. Basically, they were statistical algorithms created that we should do this, and we should find this feature. So that was called feature engineering. So for people who don't know, before the boom of DL came in 2012. What we usually had in ML was even if that is NLP or that is speech recognition or that is CV, you had some methods which you used to extract features, which is shift, Harris corner detection, NLP. In speech recognition, that would be phonemes, in so something like that. And then you use these features, you directly feed the features to an ML algorithm to do your task. But today we have deep learning, which is called end-to-end, where you directly feed the raw data. So if I say for speech recognition, you directly feed the raw audio instead of doing feature instruction, or CV you directly feed the images instead of extracting edges and corners and feeding the edges and corners. You tell the DL method ki no, I am not going to give you this human knowledge of edges and corners, you figure that stuff out yourself. Okay, this is important. This is the learning paradigm. We are telling it to learn this, but people have made the mistake that they have stopped there, which I will talk about anyways. But today all this is discarded. Modern DL neural networks use only the notion of convolution, CNNs, and certain kinds of invariance, translation invariance, and perform much better. True, that I agree. We are much better than before, but it's not enough. This is a big lesson. As the field, we still have not thoroughly learned it. Agreed, as we are continuing to make the same kind of mistakes. To see this and to effectively resist it, we have to understand the appeal of these mistakes. We have to learn the better lesson that building in how we think does not work in the long run. Very important, I'll talk. The bitter lesson is based on the historical observations that AI researchers have often tried to build knowledge into their agents. Correct. This always helps in the short term and is personally satisfying. Yes, basically the researcher feels we have done something and this leads to SOTA, and then you just publish a paper. But in the long run, these methods do not scale, they are not able to use compute, and performance does not improve. And breakthrough progress eventually arrives by an opposing approach based on scaling computation, where you use search and learning. I would say mostly learning, not search, because search is used in games, but search is not used in CV or NLP or speech recognition. So I'll say mostly. The eventual success is tinged with bitterness, true, and often incomplete digested because it's success over a favored human-centric approach. This human-centric is very important, which we'll get to. I think that was not good. This would have been better. Yes. One thing that should be learned from the bitter lesson is the great power of general purpose methods of methods that continue to scale with increased computation. Again, I have talked, all methods are not easy to scale, so you want methods which are able to better use the computation. Even as the available computation becomes very great. The two methods that seem to scale arbitrarily are search and learning. Yes, that is true, but even depending on the architecture you have, some architectures are better. Now, this is the second point which people don't talk about. I don't know why. This is more important, and I think this is the key to intelligence. It is a question which is being asked, the answer is difficult. The second general point to be learned from the bitter lesson is that the actual contents of the minds are tremendously, irredeemably complex. We should stop trying to find simple ways to think about the contents of the mind, such as simple ways to think of space, object, multiple agents, or symmetries. All these are part of the arbitrary, intrinsically complex outside world. They are not what should be built in, as their complexity is endless. Instead, we should build in only the meta methods that can find and capture this arbitrary complexity. Essentially to this method is that they can find good approximations, but the search for them should be by our methods, not by us. I'll get to this. We want AI agents that can discover like we can, not contain what we have discovered. Building in our discoveries only make it harder to see how the discovering process can be done. Now this is very important, and this is, people need to hear this. Okay. So what is the problem with the learning paradigm? What you have is, you have an input, a limited input. Okay, what I mean is your training data set will always be limited. Training data limited. And you have an output. And there is some process. And what in DL we are trying to say is that given the input and output, figure out the process. That is learning. Basically, before we were telling it what the process should be, we are saying this, tell me what the process is. The problem is when you have a limited training data, there are many spurious correlations or many shortcuts which exist which will allow you to achieve good performance on this input-output data you have collected, but is not the actual process for intelligence. Okay, so you understand, for a set of input-output you have multiple processes exist and you want the right one. There are some which would work for the input-output, but when you generalize it, they would not generalize well. But so how do you find the right process? That is an unanswered question. What people have been doing is, we see our mind. So we have our brain, we see some image, and we say it's a cat. Can you really tell me how you knew it was a cat? I mean, you can say that you can say the cat has these features and these features, but those are the products of the process that happened in your mind, which people are not understanding. Products of the process. The process, whatever computation or whatever your mind did, it led to you seeing the cat as it is. You can see the cat's eyes, the whiskers, the texture of its skin, and that. But you do not know the process. And therefore, what we have been doing is we have been trying to mimic the product, not the process. And the thing is, the product can be mimicked without actually finding the actual process. And because if you don't find the actual process, see, if you want to solve that only task now, that would be okay. But as you go talk about intelligence, you want to generalize, that becomes a problem, because that method, that process you found is not generalizable. So the whole point of that, what you want to do is you want to use neuroscience to understand how the brain works, which we don't know. You want to find general principles of intelligence. What general principles does the brain use to compute? So I'm posing a question, I'm not giving an answer because we don't have the answer. If we had the answer, we would have solved intelligence. But what we need to understand is we have always been trying to solve product. Can I match this product? Can I match this product? So if I go again to this line, that worked the way researchers thought their mind worked. So again, the researchers are thinking, if my mind works, but you do not have access to the process of your mind works. You only have the product. So even if you solve a mathematical problem, you say, okay, no, I have access to how I'm solving the mathematical problem. True. But you have many abstract concepts and symbols which you are using for mathematics, but you do not know how your brain generated that. That is the thing. If you have a small mathematical limited problem, you can make a symbolic EI and the symbols you directly implement. But in general, you have many symbols and concepts or abstractions about the world. You don't know how they were generated, but you want the model to generate it themselves, which we don't know. How we think. So we think. So again, the problem has been people think we know how our brain. We don't know. Like, don't try to imitate the product. Find how the process works, which is hard. And yeah, the contents of our mind are tremendously, irredeemably complex. We don't know how it works, and therefore we don't want to think of our mind as simple things. We want meta methods. So we want methods which find out how the mind works, like how to learn. Okay, not just telling it how to learn, but the search for them. Yeah. So again, this important line is saying is we don't want it to learn knowledge. So see, people all confuse intelligence and knowledge also. Intelligence, skill, and I have already told, right? Skill is how to solve a task. You can always cheat for a task by giving hints, priors, more experience. But generalization or intelligence about skill acquisition efficiency. Now, what is the difference between intelligence and knowledge? So an intelligent being may not have knowledge, but it has the correct process to acquire and understand the knowledge. But a knowledgeable system may not necessarily be intelligent because it just has the knowledge, but it cannot acquire more knowledge. So for example, a crude example would be like a database. It has a lot of knowledge. Is it intelligence? I think everybody agrees it's not, because it does not know how to acquire intelligence. On the same thing, I would say LLMs have a lot of facts. They can memorize. They are very good compression machine, and they are very good at approximate retrieval retrieval and giving answers, so you feel impressed, but they are not intelligent. They have no understanding. And so yeah, so what the history of AI has been, people feel that this is how intelligence should work, and they are just creating methods and methods. I think we need to be more humble, read neuroscience. I don't know what the state of the art neuroscience is, but more understand, find how Newton discovered the general laws of physics. I would say maybe not all, many other physicists contributed. So you want to find the general principles of intelligence. What are the principles which enable intelligence? I think that is what we should focus on, which nobody talks about when discussing the bitter lesson. Okay, let us go to the before we go to the better lesson, which was posted I think a few weeks or days by Rutney Brook, another respected researcher in AI. But before that, let me just talk. Yeah. So again, we want the models to learn everything on its own. We don't want human priors in it. We don't want human or anthropic or human-centered understanding of the world. I'll tell you what I mean. So one thing you have to understand is we are not the only intelligent being. All other animals are very intelligent because they survive in the real world. I am not going to go into now, but I think people don't actually understand how hard it is to do mobility, dexterity, perception. Moravec's paradox is hard because it is actually, this solving chess is easy. It is hard for us because we cannot have infinite compute and we have to reason. But what we acquire by the age of 3, this mobility, perception, dexterity, that is the hard part, and that is what we should focus on, which even Turing said in his seminal Turing test paper. We'll get to that. Before that, I want to show this. This is a paper by Philip Pineski in 2016, unsupervised learning from continuous video in a scalable predictive recurrent network. I will not go into the architecture now. I think this is a very important paper which everyone should read, but I will talking about the criticism of ImageNet it has. So this is the dataset ImageNet, and all these 6 images are labeled as aeroplane. But the thing is, for each image you need to have some contextual and social understanding of the, or dynamical cultural knowledge of the world, as he's written or they have written. So for this you need to know that plane is an object which flies. How would you know, like you understand, like aeroplane is just not an object. Maybe I don't know, I'm very bad at drawing. Okay, it's just not this object. It is an object which can fly. Now this is inside of an aeroplane, so you need to have an understanding that aeroplane is one of this vehicles or instrument of transportation which has very complex cockpits inside. How is a model supposed to know that, or any AI system supposed to know that without acquiring common sense, I would say, or cultural understanding of our world? Like this person eating, so we have aeroplanes where you can order food and eat. So this is a cultural thing, right? How can you just train a model, give it images and tell it this is a aeroplane? I mean, people do not understand that you are asking the models to do something impossible. Actually, a model should be learning like a child, getting to know that this world exists. There are objects like aeroplane which people travel in, and you also get food in. So therefore, because this person is eating, he is in some vehicle, and because this window is something like this, therefore I would say this is the aeroplane. Again, aeroplane fly in the air, so when you look outside you see ground, and again this is a part of an aeroplane, not the whole aeroplane. So something like that. That is one thing. So if I talk about common sense, again, one thing we have in our AI culture is we are always applying band-aids. That's what I think is. So as all of us can see, this is this is the basketball, and it is actually the same basketball which has been taken different snapshots. By the same basketball, there is only one light source in the room, and the ball is rotating. So depending on when you took the snapshot, the same ball can look very different, right? I mean, these are very different pictures. I mean, this one looks like a bit like watermelon, I would say, but other than that, all are clearly basketballs. But they look very different, right? This and the color change over here, the color, illumination, the shadows, everything is changing. So the what you want is a model which figures out that the same object can look very different, that a same object depending on the illumination and shadow can look very different. That is what you want the models to figure out, and we actually don't know how our brain perceives the world. That is, we don't know how to do that. I guess that is that for now. So again, I think Turing. So I think should I write child? If I write child, I think it will come. No, not this page. Just give me a second. Okay. Yeah. So the Turing wrote this. I mean, I think this paper was in the 1950s or 50 only. So this is what he wrote. I mean, the Turing test was just his proposition of how we can test intelligence. It is a very bad test. It is like you're just mimicking intelligence. It's like it is a test for, like, even counterfeit intelligence can beat it. Like LLMs beat it, or even ELIZA. If people know about it, people should read about ELIZA. Even that could beat a Turing test, and Turing test is always limited. You have to fool people. It has nothing to do with intelligence. Anyways, let us look at what Turing said. And I think this is what many researcher, a great researcher he is, or he was. This is what people should focus on. So instead of trying to produce a program to simulate the adult mind, why not rather try to produce one which simulates the child's? If this was then subjected to an appropriate course of education, one would obtain the adult brain. Presumably, the child brain is something like a notebook as one buys it from the stationery. Rather little mechanism and lots of blank sheets. Mechanism and writing are, from our point of view, almost synonymous. Our hope is that there is so little mechanism in the child brain that something like this can be easily programmed. The amount of work in the education we can assume as a first approximation to be the much as same of human child. So what he's saying is, you try to create a child mind and you give it the appropriate education, maybe I don't know, K to 12 standard, and it becomes as smart as an adult. But for that you would have to implement this child mind as an it exactly is, which we don't know. We don't know how the child mind works, and that is the first one thing. Okay, there are some things which he says which are nuancedly wrong, I think, which I would like to point out as of our understanding today. So he says the child brain is like a notebook. So what one paradigm Sholay talks about is, in DL we are assuming that we always have a randomly initialized model and we train it, and before we had knowledge system where we had a lot of task specific modules. So our brain is not task specific modules, that is clearly known now. I won't go into it, please read the paper and some more neuroscience. Anyways, one thing is, our brain is also not randomly initialized. We have some human priors which I can't recall top of the head. Sholay defines in it. So our brain has some priors inbuilt. So even Sholay talks about, when we are comparing AI system and humans, you should check if the AI systems have the human prior or not. If it doesn't have, then humans have an advantage, and how to hard code or how to put that priors in AI system, that's a hard problem. But yeah, so there human brain, what I want to say, basically it's not a blank sheet. There are some priors which exist in humans. Sholay has written about that based on development psychology. I haven't read into that, so I don't know how correct it is, but this is something which we should know. Like, people before assume task specific modules, and even Marvin Minsky, again a great researcher, assumed that, and a lot of research led to that, and of course it didn't work out. And on this task specific, he wrote his books, The Society of Minds, which people also should read more about. And yeah, and now we believe in this randomly initialized. So he talks about how both these are wrong, and this is just one of the factors which is limiting us from achieving intelligence or solving intelligence. There are many which we need to figure out as a community. Okay, yeah, and so that is that. Our hope is that there is little mechanism. Okay, no, the mind is very complex and we just don't know how to program it. So here Turing was just trying to be optimistic. That's okay. And yeah, and then your hope is that if you provide the same education, you get a human adult. Okay, that is okay. But one thing we have to understand is, even our models are very data inefficient, and they generalize poorly, but they are also data inefficient. Like I said, no, there is a child which studies 2 hours and 10 hours. So like that, our LLMs, they have seen the whole internet and even a lot of private data, and they make so simple stupid errors. Like, it should be appalling to the AI community. Like, it should leave you with disgust that we are doing the wrong thing. I don't know why people don't see it. Like, you see, it is not about like if you give it a complex problem. Like, I'm sure you can give today's state of the art LLM some complex calculus chemistry problem and they'll solve that, and even you won't know how to solve that. But you have to understand, it's not just about which problems they solve. You have to it's not just about which problems they solve, it is about which problems they get wrong. And you don't want to do it in numbers, so you don't just want accuracy. What you want is which problems, because see, every problem has a different complexity. So what you want to understand is which are the problems it is getting wrong, and if it is getting wrong problems of easy complexity and getting problems of harder complexity right, but can't do the harder problems when we change the values, that means LLMs are not reasoning, they are retrieving. They are very good at memorization. I mean, the NYT Open AI case, and you can see LLMs, if you do 2-3 passes of the same data, they can say it verbatim. Like, verbatim means word to word. So if any intelligent system, if it was very good at generalization, it could not be able to say such thing verbatim. I'll tell you why. Because it would not be able to read text verbatim, because inherently any text, like whatever we write a text, it is noisy. Like, there are some idiosyncratic ways we all write text which are not important to remember. Like, if you read a text, you can't tell me word to word, but I'm sure all humans can tell you the gist of any text. So those are compression very good remembering machines. And the thing is, if you're very good in memorization, you can't do reasoning. Like, if there is a child which can remember the whole maths textbook, and the school only asks questions from the textbook, which I think happens in many schools. So why would that child ever learn how to reason? Because if he has such a eidetic memory or good memory, he won't be reason. So that is the case with LLM. I mean, there is a lot of problem with LLMs, and I think particular people should follow Subbarao Kambapati and his talks, I think the people would have better understanding of LLMs from there. Many people haven't read his work, so that is the thing. Anyways, so as I was saying, what you want is you want to understand how the human brain works, which we don't know, and then model the learning process, which we don't know how it happens, and then then you just create a system which has all the right principles of generalization, and it learns everything on its own, other than the human priors which are present in humans, and then it would be able to acquire common sense and do different tasks. That should be the ideal goal, which I don't think many people are doing. Anyways, okay, the better lesson by Richard. Okay. This he also raises important points. Just last week, a better lesson. Rodney Brooks, sorry, I think I said Richard by mistake. Last week, Richard published a very short blog post titled "The Better Lesson." I'm going to try to keep this review shorter than his post. Sutton is well known for his long and sustained contribution to RL. In his post, he argues, using many good examples, that over 70-year history of AI, more computation and less built-in knowledge has always won out as the best way to build AI systems. This resonates with the current mode of thinking among many new entrants to AI. This is a problem in AI, that we have had a lot of boom and funding, and hype, which I think is okay. It's good for the overall field, but we have had a lot of people who have not read history of AI and don't understand how hard intelligence is. And it's like they are making the same mistake. Like it's like, the quote or whatever, the history is bound to be repeated, or so basically those who don't know the history repeat it. So I think every research scientist, engineers are different, but every research scientist in AI should read AI history. They are making the same mistakes as the past, whatever. And if we are making the same mistake, we won't make progress. We have to actually learn what they did, why it didn't work out, and then use that perspective to do better work. It is better to design learning networks and put in massive amounts of computer power than to try to design a structure for computation that is specialized in any way for the task. Okay, again adding priors. I must say, okay, one more thing. Yeah, so we have LLMs, right? I don't have all the papers now, but we have many LLMs which are trained on all the text. But there are many, if you fix the task now, there are many old NLP methods, not DL, or I would say specifically LLM, generative AI methods, which do better than this computation LLM. So LLMs are trained on a lot of data and a lot of computation, but this old NLP methods we have, or you can say standard, I don't know, classical methods, they do better. I don't have the list of the papers, but I'm sure people from NLP community can talk or point out papers. So it's just computation is not working. I'm telling you, in many specific tasks, adding priors. So you want models which have computation, but even adding priors. So both of this helps. So it's not just you don't want to put human knowledge, less human knowledge, some prior, and more learning. But people are not doing enough learning. We are still focused on human-centric learning, that I would add the knowledge. So even one problem with language is not the real world. It is the understanding of the human world, understanding of the real world as by humans, and each word has a big abstract concept behind it, which the models or LLMs or VLMs never got to learn because they are not embodied. If I say the word fall, you understand it, but how can an LLM or VLM understand fall without what do you say? I mean, seeing objects fall. Like, how can it understand that there is an object, that if there is no surface it falls, or if you throw it falls? Again, I think these things are not philosophical. I mean, people will point out the Chinese argument, qualia and consciousness, and go into all that stuff. The only point I want to make is I think this is core to intelligence, that you can just not understand words. So language is embodiment, means basically high bandwidth, constant high bandwidth sensory input or access to the world. So that would be vision, touch, or smell, or any of them. Like what wavelength we see, other animals don't see that wavelength, they see different. Some rely more on smell or touch or whatever, but they all are embodied and they are all intelligent. Language is for communication and thought, but language is not how you reason or understand the world. So LLMs, even if everything was right, which is not right, let's just say you have the best AI system, or the correct AI system, the correct architecture, the correct laws and paradigm, everything, LLM still won't work, because language has nothing to do with common sense or intelligence. I will expand on that later. I'll write a paper on that. Anyways, I must say, I must say, however, that at a 2-day workshop on DL last week at National Academy of Science, the later idea was much more in vogue, something of a backlash against Sutton is arguing. Okay, let's see. I think Sutton is wrong for many reasons. One of the most celebrated success of DL is image labeling using CNN, but the very essence of CNN is that the front end of the network is designed by human to manage translation invariance. The idea is that object can appear anywhere in the frame. So true, this is a prior edited by AI researchers. The model didn't learn itself. To have a DL network also to learn that seems pedantic to the extreme and will drive up the computational cost of learning by many orders of magnitude. This is where I disagree with Rodley. He, as of the current methods we have, it is true that it would drive up the computational cost of learning, but we don't have the right methods which are efficient. I mean, humans don't need a lot of data for learning how to perceive the 3D world, or other animals don't require it. I know Jan LeCun has made a post about on that. I think his post is wrong. You cannot quantify the data the way he talks about. He talked about in Davos and he posted on Twitter. I won't go into that. I mean, you can just read the quote tweets of that tweet, and Chomba Bupe and many other people talk about how he's wrong about that. Anyways, not get into that at the moment. There are other things in image labeling that suffer mightily because the current crop of CNNs do not have certain things built in that we know are important for human performance. Color constancy. That is why the celebrated example of a traffic stop sign with some pieces of tape on it is seen as a 45 mile per hour speed limit signed by certain CNN trained for autonomous driving. So again, these are adversarial examples. Now I am not aware much about color consistency or how humans see, but again the important question a AI researcher should ask is this inbuilt in the brain? Like, is this the prior of the how the way the brain is designed, like translation invariances, or is it something the brain learns that? So that is what we want to know. So if that is how actually the human brain works, we insert that prior. If it's not, we find out how it learns, which is very hard. Anyways, but that is what you should do. Ideal. No humans make that error. And again, this all is important if you want to solve intelligence. If you want to solve DL, you want to solve a specific task, then don't get into this. Okay, intelligence is hard. Anyway, no human makes that error because they know that stop signs are red and speed limit signs are white. Again, this is common sense. Models have to learn how to acquire them. We don't know how to do that. You can't tell model all the knowledge. Like the problem with common sense is because it is common, humans don't talk about it generally, and lot of it is innate. Like it would be obvious to you for you if I tell you and you would say obvious. This is obvious, of course, this is common sense, but you can't tell all this to the model because you have learned yourself. Like how much do parents tell about their children about the world? Like it is high level supervision. We don't tell it each little thing. We don't tell it if there's an umbrella, we don't tell it every feature of the umbrella. We just say this is an object which is used to protect from the rain, and this is we call umbrella, and the child easily learns through 1-2 examples and can say no, this umbrella and all umbrella are same. It doesn't need to see this is black and red, so no, I need to see multiple training examples. It doesn't work like that. Anyways, so we are basically very efficient. That's what I'm trying to say in data terms and lot of terms. The CNN does not know that because the relationship between pixel color in the camera and the actual color of the object is very complex relationship does not get elucidated with the measly tens of millions of training images that algorithms are trained on. Again, I think there are two problems with this. Is first of all, so I don't know what is the FPS of the human brain. Again, you need to know that, so to see how much data the human brain takes in. But we master our vision, if I'm correct, by 3 to 5 years. If there is any someone who works on vision, a neuroscientist or someone like that, and knows if I'm wrong, please point it out. But if I know we master our vision, so you can't say like after the age we master our vision, or mostly master, you can't say more training data helped us, right? I mean, if you have mastered a problem, seeing more of it is you're not learning anything new. So I think people first need to put age of when we master vision, and then not look in data more that. I mean, Jan LeCun says 4. Why does he pick age 4? I mean, why not pick age 3, 3.5? So I think you need to stop where we master vision. That is one. Again, the data is not embodied. When you see a frame or you see a continuous time, so people have to understand that temporality, time is a property of the world. Time is how world exists. You cannot learn about illumination, shadows if you don't have time. So we have to give continuous images, not just random images. How would you learn about the facts? Data augmentation or synthetic data is a band-aid because we are not doing fundamental embodiment. Saying that in the future we will have viable training sets is shifting the human workload to creating massive training sets and encoding what we want the system to learn in the label. Again, the AI systems, like even there is no ingenuity of AI. We have so big training sets, that is ingenuity of humans. And if I talk about it, open AI company or other company, I mean, of course there is no proof, but they are using all this they are paying workers in what do you say, I would say the global south, and let's just say, people are being exploited. That's what I'm just trying to say, to make all this training data, and then the jobs are being taken like illegal data, all the work taking data from the artist. I mean, it's appalling what all OpenAI and all these companies are doing. Of course I don't have proof, don't sue me, but you know what you're doing. Okay, I mean, just a few days ago Brad Lightcap was asked if Sora is trained on YouTube, and for 2 minutes he talks but doesn't say anything important. I mean, those guys are cowards. They are what they are. Anyway, researchers should focus on research, and the cowards are cowards. Anyways, so all these data sets are being created by us. This is just as much building knowledge in as it is would be directly to build color consistency stage. It is a sleight of the hand in moving the human intellectual work to somewhere else. In fact, for most machine learning problems today, a human is needed to design a specific network architecture for learning to proceed well. So again, rather than have the human build in a specific knowledge, we expect the human to build the particular and appropriate network and the particular training regime that will be used. Once again, it is the sleight of the hand to say AI succeeds without humans getting in the loop. Rather, we are asking the human to pour in their intelligence into algorithm in different place and form. Yeah, again, two things. I don't think what do you say, Richard says that AI succeed without humans getting in the loop, but that is true. Other people, I think, they are overestimating. Like AI researcher, all this thing is happening. What training laws to decide how to feed the data, all that has happening. Do not confuse the ingenuity, because a lot of things are created, the AI systems are created by us. Don't give all the credit to the AI system. I think that is where people are being confused. And the layman understanding of public, people think AIs are agentic. Like, they don't understand that AIs are static systems which have to be told everything by us. Massive data sets are not at all what humans need to learn. Again, we are more efficient. Today, data set can have billions of examples where human would again require handful of things. But worse, the amount of computation, again, not even data efficient, not even computationally efficient. This is not sustainable for getting intelligence. Yeah, and our carbon footprint is increasing, and a lot of research has been done. If I remember the Bloom paper, the LLM produced, the authors, if I remember, it's okay, I don't remember the name of all the people, but Timinit Gebru, and you should check all people who work like her, or how much carbon footprint is being done. I think she can point to the right people. I think it's Sarah Luconi. I forgot her name, so I think that's her name is something like that. She has done a lot of good work on carbon footprint, and people should look into it. Moore's law is slowing down, of course, yes, and we don't know how this computation will look. I think the bitter lesson should actually be called the bitter lesson, because what is happening, because of computation, AI researchers are not trying to solve intelligence, and they are just riding the computation. Like, just put more compute, put more data, get SOTA, publish. Nothing to do with intelligence. Like, I think the people will call the bitter lesson the bitter squared lesson, because it was, the compute was a disguise. It was misleading us, because we will never figure out intelligence until, like, researchers get an external slap that no, compute is now limited, and actually find out how to make models efficient. And again, like, they are not compute efficient, they are not energy efficient. So that's what he's talking about. I think I'll finish up fast. Computer architects are okay, again, this 6th point is very important. This is the hardware lottery, which I forgot who wrote that paper. That is a very important paper people need to read. Computer architects are now trying to compensate for this problem by building special purpose chip for runtime of used of trained networks, but they need to lock the hardware without changing the result. This has two drawbacks. It locks the hardware for particular solution, and so every time we have a new method, we design new. And so yeah, there's two things. First of all, when we have new hardware, like, people have been proposing new hardware for transformers, where this chip is specialized for transformers. So okay, that is okay, but the problem is that because such specialized chips have been proposed, instead of trying new methods, people will just try to be used that because this algorithm is compatible with the hardware. That is what hardware lottery means. This algorithm becomes popular because it is compatible with hardware, not because it is intelligent or it is better. That is one problem. And second is because this all chips, like creating chips and all this are very complex. So all this computation has been, again, human ingenuity, not AI. That is, I think, what people need to understand. And again, this hardware lottery is very important. Please read. So my take on Richard Sutton's piece is that the lesson we should learn from the last 70 years of AI research is not at all that we should just use more computation that always wins. Rather, I think a better lesson to be learned is that we have to take into account the total cost of the solution. Yes, correct, and that so far they have all required substantial amount of human ingenuity. There is no agency; it cannot do a lot of things itself. Saying that, okay, saying that a particular solution style minimizes a particular sort of human ingenuity that is needed while not taking into account all the other places like data sets and carbon footprint can expand into terribly myopic view of the world. This review, including this comment, is 76 words. Okay, whatever. See, one important thing is so GOFAI means good old fashioned AI, which is basically symbolic AI or having a knowledge system. So what I think is people don't even understand. Like Hinton and all this, they were against this good old fashioned AI. They wanted learning in neural networks. But LLMs are, if you see na, they're actually good old fashioned AI. You just have it, what is this all text? These are just big knowledge bases. They memorize them, and LLMs are just better symbolic manipulators than the ones we have old. So they are interpolative. So they can, if you ask something, so they are able to write some text bullshitting and using statistical probability. But again, what I'm trying to say is just LLMs are good old fashioned AI in disguise. So Hinton tried to do all that, but it didn't even lead to that. And one more thing is people don't understand how hard intelligence is. It's a game of statistics versus dynamics, which I think people should read more about from Philip Pineski's blog. Yeah. So I think this person he has written a lot of important things which should be more spread as a common knowledge if people want to solve intelligence. So I urge people again to look into his blogs, and again the unsupervised paper I showed, the PVM where the ImageNet and the basketball, that paper again I urge people to look into. I hope this was a good talk, and I hope I have left you with more questions compared to answers. We need to ask more questions. We are researchers.